Okay? So in dealing with equilibrium, we've been talking about how these reactions go from reactants to products, but we understand that these reactions can be reversible, meaning they go from products back to reactants. And we say that eventually they don't come to a stop, but what happens to the reaction? It comes to a point where there's no net change. Awesome. Okay. And so the idea is that your reaction is basically going forward and backward at the same time. Yeah, or rate. Perfect. It's happening at the same rate now. Okay. Now keep in mind that equilibrium in K does not tell us anything about how fast the reaction is going. Instead, what does K tell us? It basically just tells us whether we are favoring products or favoring reactants at equilibrium. Awesome. Okay. So once you reach equilibrium, are you favoring the products or are you favoring the reactants? Now, the equations can be used. You can have random concentrations that are put into the equations. If you do, you no longer call it K. Instead, you call it Q. And that's called the reaction quotient. Okay? And the same thing's going to apply when we do Ksp and solubility. Okay? So first, let's take a step back for just a minute, and let's talk about this idea of solubility again. Okay? Because now we're not going to be talking about a reaction happening. Instead, what we're going to be talking about is something being soluble. What does that mean? Does it dissolve? And for the most part, we're going to be talking about whether or not it dissolves in water. Awesome. Okay. So we're going to be talking about is, does it dissolve? Now, we had our full solubility chart, okay? And our solubility chart had things like the nitrates and the acetates are all soluble, and then we had things like the sulfates are all soluble except for silver, lead, and mercury, okay? And then we had the caserba, calcium, strontium, and barium. So we had those. We had the AgBrs. We said those were all soluble except for silver, lead, and mercury. And then you had the opposite. You had the ones that were insoluble, but then they had exceptions that were soluble. So what we're going to talk about is those particular ones that are insoluble, or so we're calling insoluble. Because really, what do you know about an ionic compound and when you put it in water? Well, it's called an ionic compound because it's going to break up into what? Ions. Okay? And almost all of the ionic compounds do. But they may do so very, very a little amount. So a really small amount may be dissolving in water. And so we say that the solubility, we say it's insoluble, but really some of it may actually be breaking up into ions, and it's just a very small number. Okay? So what we're going to do is we're going to compare our reactants to our products. But in most of these, what we're going to notice is if you take your reactant that's a solid and you dissolve it in water and it doesn't really break up much, what are we favoring at equilibrium? The reactants. Perfect. And if you're favoring the reactants, is your number going to be bigger than 1 or smaller than 1? Less than 1. And do you think it's going to be slightly less than 1 or much, 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 much smaller than 1? Much smaller than 1. And you're going to see that these Ksp values could be something like 10 to the negative 8, 10 to the negative 10, 10 to the negative 12. They're going to be such small numbers, but that just means that you're favoring your reactants that much, okay? As your number gets bigger, if you get a number like 2 or 100 or 200, what does that mean? That means you're favoring your products, okay? And if the number is super, super high, we don't even talk about having a Ksp value. They just don't do it. They just say there is no Ksp value because the whole thing completely ionizes, okay? So if you're talking about something like salt, what do we know that NaCl does? It completely dissolves because we said the alkaline metals, those 1As, those are all soluble, right? So the ones that completely dissolve, the whole thing is going to break apart and you're not going to talk about having a Ksp. So if we do this simulation here and we drop some of the NaCl inside of here, then again what we end up seeing is we see that these salt molecules, these green ions and these red ions, everything is separated. Na plus and Cl minuses have all pretty much separated from one another. Okay? So let's go to a slightly soluble salt now. So we've got mercury 2 bromide, silver bromide. Let's take a look. I like silver bromide. I think that might be a good one too. Let's take a look at that. So we're talking about AgBr. And what do you know about AgBr, the bromides? They're all soluble except for silver, lead, and mercury. Okay? So I'm going to drop some of this silver bromide inside of there, and let's just take a look to see what happens when we drop it in here. Okay. Is some of it breaking up?
Yes.
Yes. Some of it is breaking up, okay? But what ends up happening is most of it doesn't. And so what we're going to talk about is that solubility product constant, is how much of it will precipitate versus how much of it is going to ionize. So when I say this word precipitate, what does that indicate? What does that mean to you? That's what inside of what? A solid inside of a liquid, okay, inside of water, for example. And so that's a part that does not dissolve, that's actually going to stick together. Okay? All right, so let's take a look at the notes and start filling in some of the notes. So it says solubility is a very important phenomenon. It's the chemistry behind dissolving sugar and salt to flavor foods, reducing tooth decay, or viewing x-rays more clearly. For example, if you want to improve the clarity of x-rays of your GI tract, and some of you maybe have done this before, you can take something called barium sulfate, which actually, the ion barium is very toxic to us, okay? It would kill us. But the idea is barium sulfate has a very low solubility, which means a lot of it is not doing what? Not dissolving. It's not breaking up into ions, okay? So because of that, we're not so worried about that barium ion, and it actually makes it safe so that we actually can ingest it, and then they can highlight our GI tract if we need to, if there's some issue that's going on. The oceans are salty because salt dissolves in water. Other minerals such as limestone dissolve only slightly, and they have low solubility, so they're not dissolving as much. Much of our fresh water contains only small amounts of dissolved calcium carbonate and other minerals and is known as hard water. So we've heard of that before, and that's going to be something that you're going to be testing in this inquiry lab, is this idea of hard water and really researching that. The behavior of CaCO3 and of other slightly soluble substances is controlled by equilibrium processes involving solubility. Okay. So we know that ionic substances can conduct electricity. That was something that we talked about when we did our MIMSI chart. And we said basically in two situations, either in the molten state or if they are aqueous and dissolved in water. Okay? So if they're dissolved in water, then for the most part they should be conducting electricity. But not if they're not dissolving. Okay, so if a lot of it is not dissolving, then you're probably not going to get that light bulb to light when you try to conduct that electricity. So it says either if they're dissolved in water or if they're melted. Look at the following soluble salts dissolving in water. These will completely ionize in water based on our solubility chart. So it says what will be the concentrations of each ion if you start with 1 molar of NaCl? Well, NaCl is going to break up into Na plus and Cl minus. You agree? So if our concentration of NaCl is 1 molar, then what's our concentration of Na plus? Don't answer it yet. I'm going to give you a hint because some people will say the wrong answer because they haven't completely thought about this, okay? So if I take NaCl, and let's say that I take 5 NaCls and I drop them into water, and I know that these 5 NaCls are going to all break up into Na plus and Cl minus. How many Na pluses will I have in here? 5. 1, 2, 3, 4, and 5. And how many Cl minuses will I have? 5. 1, 2, 3, 4, and 5. Now when you're asked about molarity, you're asked about how many moles per liter that it is. And so if we were saying that this was 1 liter and that was 5 molar to start of the NaCl going in, then how many moles of my Na plus do I have? It's still what? 5. And how much Cl minus do I have? 5. So let's come down to this question. If it's 5, then it's 5 and 5. So if it's 1, then it's also 1 and 1. Because the biggest misconception that people have is they go half. Guess why they think it's half? Yeah, because they think that, well, half of it's Na plus and half of it's Cl minus, but remember, that's not what we're saying. We're saying how much Na plus and how much Cl minus. So they end up being equal to whatever your concentration is. So let's see what happens with Na2CO3, which also is going to ionize completely. So if this is 1 molar, then what's your Na plus concentration? 2 molar. Very good. Why is it 2 molar? Because it's a 1 to 2 ratio. You're going to get 2 Na pluses for every 1. So when you drop it in water, every single one of these is going to give off 2 Na pluses. So now you've doubled that molarity of it. And what's your CO3 2 minus concentration? 1 molar. It's really important that you understand this idea because it's not a chemical reaction. Okay, what this is now is you're going to take a solid and your solid is going to break up into the ions. Okay, so I wanted to make sure that we first talked about something that did ionize completely before we talk about something that doesn't. Okay, so generally compounds of alkali metals are soluble in water. We know that. Generally, many ionic compounds are insoluble, like the phosphates, like the sulfides, like the sulfites, like the carbonates. Chromates were also on our chart. Hydroxides, do you remember what the strong bases were? We said that hydroxides are all insoluble except for, do you remember? 1As and? 2As. Not all the 2As. Caserba. Very good. 1As and caserba. Okay. So the sulfides were the 1As and the 2As. Okay. And ammonium was thrown into there. So also don't forget the strong acids. So don't forget what those strong acids were, because remember, hydrogen doesn't fit in with the alkali metals. Hydrogen is pretty much its own family. It kind of does its own thing. So when something starts with an H, we call it an acid. What were the strong acids? I-clabber, No3, Clo4, Sulfur. Everybody say it one more time. I-clabber, No3, Clo4, Sulfur. Awesome. Okay. And those are the ones that do break up into ions. So it says, however, most insoluble salts will actually dissolve to some extent in water. And what we call them is we call them slightly soluble in water. We say that they're slightly soluble in water. Because the solid amount is not really changing, we simply incorporate it into the constant, just like before. We said we don't use solids and we don't use liquids. Awesome. We only use gases and aqueous substances when we're doing equilibrium expressions. Therefore, just as we said when dealing with KEQ, the solids and liquids are ignored. Sorry, I was supposed to say and. Solids and liquids are ignored in the expression. So, the solubility product constant. It's basically KEQ times your reactant is equal to the Ksp equal to the products. And here's why. So our K we know is equal to concentration of products over the concentration of the reactants. But what do you notice about the reactant? The reactant is a solid, so instead what happens is this reactant actually gets thrown right into your K, okay? So instead, our Ksp is simply equal to the concentration of your products, which are ions. Does that make sense? Okay? So we don't have to put any reactants when we're doing Ksp because the reactant is a solid, so we're not going to include those. Please note the difference between what is called solubility and what is called solubility products, okay? There's a difference. When you say how soluble is something, you're basically saying how many grams are going to dissolve per milliliter of it, okay? Or how many moles are going to dissolve per liter of it. You could use concentration as a unit of solubility. You could use grams and liters. So it's basically how many grams dissolve per liters, okay? And you can change your grams to moles. When you're talking about the solubility product, now what we're talking about is how much of the reactant is dissolving, okay? And so the number that you're going to get, this K value that you're going to get, is going to tell you, are you favoring your reactants or are you favoring your products? And more than likely, you're going to be favoring your reactants. So your number is going to be smaller than 1, a lot smaller than 1. So the solubility product is an equilibrium constant. It's a constant. And it has one value at a given what? Temperature. One value at a given temperature, just like we said before. What can change your K, EQ? Temperature. Perfect. Solubility is simply an equilibrium position, and that's going to be how much dissolves per liter, for example. Okay? So that's basically what this is telling us, solubility. Let's see if we can calculate it now. So calculating solubility. Question 1 says, write the equation for AgCl dissolving in water. Then let's write our expression. Okay, so AgCl, solid, is going to break up into what? Ag plus and Cl minus. Awesome. And now let's write our Ksp expression. So Ksp is equal to concentration of our products, which in this case is going to be what? Ag plus times Cl minus. Remember, you're not adding now. Okay, you're multiplying. Divided by what? Nothing. Our reactant is a solid, so we don't include it. That's it. We're done. Okay? So don't include that. That's it. What is the concentration of Ag plus and Cl minus in a saturated silver chloride solution at 25 degrees Celsius? And they're giving us the Ksp value. Okay, so we know that our Ksp is equal to the concentration of Ag plus times Cl minus, and they're giving us the Ksp value, and they're saying that it's 1.8 times 10 to the negative 10. Okay, no units, same as last time, no units. It's just telling us which direction it's favoring. By the way, 10 to the negative 10th, what's that favoring?
Reactants.
Reactants by a lot, right? Okay, so that's a really, really small number, so we're really favoring the reactants here. All right, they're not giving me any more information. What do you use if you don't have any numbers to use? X. Awesome. And if I call this X, then what would you call that? X. Perfect. Because when AgCl breaks up, it's going to break up equally into Ag plus and Cl minus. If there were 2 there, what would you be calling that? 2x. Awesome. Okay. So now watch what happens. Well, it's x times x, which is just what?
2x.
X squared, right? X times x is x squared. How do I solve for this then? How do I solve for x? Square root. So I'm going to square root both sides. Please go ahead and do this. And please tell me what you get for your value of x when you square root 1.8 times 10 to the negative 10. Now, you will have units when you're done because we're talking about concentration. So if it's concentration, what do you think your units are going to be? Molarity, which is kind of weird because you don't have units and then all of a sudden you do, okay? So you will have units of concentration. So can someone tell me what you get for this? So let's use 2 sig figs. So is it 1.3 times 10 to the? Negative 5. Awesome. And now it is molarity, and this is equal to our Ag plus concentration, which is also equal to our Cl minus concentration. But keep in mind, this is the solubility of it. In other words, this is how much that did what? Dissolved. Awesome, awesome. So what this is representing, represents the concentration that dissolved. The concentration that dissolved. Okay? All right, it says write the equation for the following dissolved in water and then write the expression Ksp for each cell. Remember, when you're dissolving in water, the solid's going to break up into its ions. We know this. Okay, so let's do PbCl2. PbCl2 solid yields, okay, and these are double arrows really when we're dealing with equilibrium because we know that they can go in both directions. So what is this going to break up into? Pb, and the charge, well, if chlorine each one's -1, then Pb must be a +2 because it could be different. So it's a 2 plus what?
Cl minus.
How many Cl minuses? 2 Cl minuses. Perfect. Okay, and let's do this Ag2CrO4 one. So Ag2CrO4 solid, do the same thing. What would this one break up into? How many Ag pluses? 2 Ag plus what? CrO4, and chromate has a charge of -2. Okay, question 3. This is, I just wanted to make sure that we did a little bit of practice with that too. So let's say that you were using x's on this. If I called this x, what would you call this? 2x, but what would you do on this one? 2x and x. Now, if they give you the concentration, don't use x, okay? If they give you one of them, you can always figure out the other one, because if we come back to the picture that we did up at the top with the NaCl, okay? If I told you that your NaCl broke up and you ended up with 10 Cl minuses, how many Na pluses do you have to have? 10. Why? It's a 1-to-1 ratio. So no matter what, but keep in mind, I could still have extra NaCl's. If it's not a fully soluble substance, I could have extra NaCl that's still in my beaker, which kind of brings us back to this. Don't forget that when I put this in here, I could have a certain concentration. In this case, was a silver bromide of AgBr that's going in. It is not equal to how much dissolved. But what is equal is every single AgBr that breaks up, you have to get Ag and Br that take off together. So if I know how many Ag pluses there are, I know how many Br minuses there are, but I don't know how much AgBr there is. Okay? That's a separate calculation because I could have a whole bunch that's still sitting there at the bottom of my beaker or my flask. Okay? So again, similar to what we said last time, You cannot do stoichiometry between your reactants and your products unless you are at what step? Change step, you guys rock. Unless you're at the change step, it's the only time that you can match stoichiometry between two sides. But if they're on the same side, then you can't make, in this case, you can't have Ag plus come off without the Br minus coming off, okay? So they're gonna separate together is what's going to happen. All right, so let's come back down to this. And so if I said, for example, that this here were 2 molar, then this would have to be what? 1 molar, okay? And if I said that this were 3 molar, this would have to be 6 molar, okay? But again, I would not be able to figure these out, but I could figure those out. So don't use X if you know one of them. If you know one of them, then there's no need to use X, all right? So it says, what is the Ca2 plus and the F minus for the dissolving of CaF2? And they're giving us the Ksp value. So let's first write our expression. So you always have to write your equation and your expression before you start. So we've got CaF2, and it's a solid, and we're going to break it up into what? Ca2 plus and 2F minus. Awesome, and 2F minus. So then it says that, let's write our expression. Ksp is equal to, remember we're going to leave out the solid, so what is our Ksp equal to?
Ca2 plus.
Ca2 plus times,
F minus.
yep, F minus
Squared.
squared. We're not using X right now, okay, we're just saying the F minus squared. So same as what we did before, right? So it says, write the balanced equation, then what's the solubility of CaF2 in molarity or grams per liter? So they're giving us our Ksp, which means that's not what we're looking for. What are they asking us for? Solubility. They want to know how much of it does what? Dissolves. They want to know how much of this stuff dissolves. Well, if you figure out how much of this there is, then that's the same amount that dissolved, but which one would you have to use? It's a trick question. Not really, kind of. If I want to know how much of this one dissolved, then which one of these should I use? The what? I heard it. Why the Ca? 1-to-1 ratio. Awesome. You want to use the Ca because that's a 1-to-1 ratio. So if you know how much of this broke up, again, that would be similar to going back up to the NaCl one and saying 5 of them, I see 5 Na pluses and 5 Cl minuses. Well, how much NaCl broke up? 5 of them broke up, okay? It's a 1-to-1 ratio. So you always want to use the one that's a 1-to-1 ratio. All right, so let's check this out. We already know our Ksp value, so we know that it's 3.9 times 10 to the negative 11. Again, there are no units on that. They're not telling us anything else in this situation. What do you do if they're not telling you anything else? You have to use X. So now we do have to use X. And if I call this X, then I would have to call this 2X. Okay? I have no choice. Again, if they gave me the concentration of one of them, I would not be using X, but they didn't. So in this case, I'm going to call this X. What are you calling F minus? 2X. Don't forget to do this also. Squared. Here's where most people go wrong. Okay? When I ask you what this is, simplify this, put it all together. What is that equal to? Take a second before you answer because I want you to answer correctly. I'm hearing 2 different answers. I'm hearing 4x squared and 4x cubed. 4x cubed. Awesome. Why? Because if you do this, you get x times 4x squared, and x times 4x squared is 4x cubed. Okay? So whenever I'm going to tell you that this is something that you can even remember, 3.9 times 10 to the negative 11 is equal to 4x cubed. So now how do I solve for x? I want to first do what? Divide by 4 on both sides. Okay? And then we get what x cubed is equal to. So, yep, and then you're going to cube root it. So I've got 9.8 times 10 to the negative 12 first when I divide by 4. And now you're going to cube root it. Please do this in your calculator to make sure that you know how to use your calculator. Okay? If you don't know how to use your calculator, then we'll have to spend some time figuring that out so you can ask each other how to figure that out. What are you getting for this?
2.14 times
2 point and 2 sig figs. So x is equal to 2.1 times 10 to the
negative 4.
negative 4. Perfect. And now what are the units?
Molarity.
Molarity. Perfect. Okay. This is equal to our calcium ion because we just solved for x. but is it equal to our F minus? Why? You need to do times 2. So that would be 4.2 times 10 to the negative 4 molar is equal to, if they're not even asking us for it, but if they did ask for our F minus concentration, then that's what that would be. Which one is equal to the CaF2 though? The Ca, perfect. That's also equal to our CaF2. Again, it's not really the concentration, it's the solubility of it. Okay, that's the solubility of CaF2. Okay, one more problem. So let's head to the back here. We've got calculating Ksp. Last thing, because we talked about how do you calculate solubility product, and then we'll do this a little bit later. There are 2 more types of problems that we do with Ksp, so I want to make sure that we go through those. But before that, let's just do this one right here. The solubility of PbIO32 is 0.0224 grams per liter. Find Ksp. So now we're solving for Ksp. Step 1, write your equation. We need our equation in order to write our expression. So we've got PbIO32 solid yields what? Pb2 plus 2IO3, and it has a -1 charge, IO3 minus. All right, and let's write our expression. So Ksp is equal to, remember you're only writing concentration of what? Products, perfect, only the products. So we've got Pb2 plus times IO3 minus squared. Good? So now they're telling us we want to know what the Ksp value is. Okay, we're looking for Ksp. We don't have Ksp. So what is this representing? If that's the solubility of it, what does that mean?
Like molar.
That's how much of it does what?
Dissolve.
Dissolves. Awesome. That's the concentration of it that dissolves, okay? But that's not concentration. That's grams per liter. What do we need? Moles per liter. So let's come over for 1 second and let's just switch that. So we've got 0.0224 grams for every 1 liter. We're going to cross our units opposite and we're going to go grams to moles of this PbIO32. So let's speed this up here. In order to calculate this, we need the molar mass of PbIO32. And it ends up being 557.0 grams per mole. So if we divide this, we end up getting 4.02 times 10 to the -5th molar. Again, this is the solubility, meaning that's how much of it is going to dissolve. That's how much of it is going to break apart. So if I know that this is 4 times 10 to the -5th molar, then what is this? Why same thing? 1-to-1 ratio. Love it. 4.0 times 10 to the -5th molar. So then what's this one?
Times 2.
Double it. Awesome. That one must be double. So it's 8.0 times 10 to the -5th. So you can see that if you missed what I talked about at the beginning, it would totally throw you off about like NaCl breaking up into Na plus and Cl minus, but like MgCl2 would be 1 Mg and 2 Cl minuses, for example. So that could really throw you off, okay? So now we have our concentration, so guess what letter we're not using to solve in these problems? We are not using X, okay? We are not using X. So you do have the concentration, so you're going to plug them in just like we did when we did KEQ, okay? We already doubled that, we already took that into account. So Ksp is equal to the concentration of Pb2 plus, which is 4 times 10 to the -5th molar, but really our units are going to go away anyway, okay? But it is molar, times 8.0 times 10 to the -5th what? Squared. Very nice, okay? So now go ahead and calculate this. 2.56 times 10 to the
-13.
-13. Are there units?
No.
This is K. There are no units. Again, all this is telling us is whether it favors the products or the reactants, and this is very much favoring what? The reactants. Okay? Awesome. And that's